First, we will look at kinematics. And kinematics is the study of pure motion. The study of pure motion. So not taking into account mass or forces, but just the study of pure motion. So here we're going to be talking about displacement, velocity, acceleration, and also speed. And we'll talk about the difference between velocity and speed later. Okay, so just starting with displacement, suppose we have an object P that moves along a straight line so that its position, we'll call that position S from an origin O, is given as some function of time. We write S equals S of t, where t is greater than or equal to 0. S of t is a displacement function, and for any value of t, it gives the displacement from O. On a horizontal axis, if S of t is greater than, here's the origin, if S of t, the displacement is greater than 0, then P is on this side of that axis. If S of t equals 0, it's right at the origin, the particle, and if it's less than 0, it's going to be over here on this side of the graph. When we talk about velocity, average velocity of an object is the ratio of the change in displacement to the time taken. Okay, so change in displacement to the change in time. Again, looks an awful lot like slope or gradient formula. Okay, but here we have it. If S of t is the displacement function, then the average velocity is change in displacement divided by the change in time. So if S of t is the displacement function of an object moving in a straight line, then we could even use this to represent instantaneous velocity, or the velocity function. Okay, and this is our derivative. So what this is saying is we have S of t, this is a function representing displacement with respect to time. With respect to time. I'll just use that little WRT, with respect to time. Now, velocity, v of t, is the derivative of that displacement function. And it is the velocity function. It represents instantaneous velocity. So the velocity at that exact instant point in time. If we look further on, then we're going to look at the acceleration function. It is the derivative of the velocity function, but the velocity function is the derivative of the displacement function, so therefore the acceleration function must be the second derivative of the displacement function. Okay, so this is the acceleration function. Okay, it's how the velocity is changing with respect to time. So just to recap once more, S of t is the displacement function. Displacement function. It represents displacement with respect to time. Velocity function is the derivative of the displacement function. Okay, so this is the velocity function. It represents instantaneous velocity. In other words, we're talking about the rate of change in displacement with respect to time. And thirdly, the acceleration function is the derivative of the velocity function, or the second derivative of the displacement function. This is the rate of change of velocity with respect to time. Okay, so we can think about now, what would the units of these functions be? Up here in our displacement function, if we're talking about distance in meters, it's with respect to time, we're talking about meters. If we're talking about velocity in our velocity function, this is the change in distance, so meters, with respect to time. Say time is in seconds. So meters per second, which is what velocity is measured in. Acceleration function is the meters per second, change in that, per unit of time. So meters per second, okay? Which better way of writing that? Meters per second squared. And often in textbooks, you'll see it as ms negative 2. Okay, negative exponent because it's in our denominator. Same thing up here. This could often be written as ms to the power of negative 1, which means meters per second. And here's the note here about the acceleration, and also a little note about the units. Okay, we've already talked about that.